Let's consider two more examples of measuring qubits in a basis. The first example that we'll consider is measuring the qubit psi, given by a superposition between 0 and 1, where we here have a complex I. And we will measure in the qubit in the basis given by plus and minus. So let me write this out. Plus being a superposition between 0 and 1, and 1 being 0 minus 1. Note that earlier I had put a minus in front, but that will not matter. Now we know by our rule that the probability of obtaining outcome plus, so again we'll identify outcomes with the basis elements, can be found by computing the inner product between psi and plus. So let me perform this calculation, and you might be tempted to think that plus and psi look almost the same. However, in our example, there's one small piece of caution here. Namely, we have this complex I. So let's compute what we get. So I'll insert here psi, which gives us 1 over square root 2, and I get another 1 over square root 2 from the plus, so I have 1½ times 0. And I'm now taking the bra of psi, and remember that the bra is the conjugate transpose. So we'll turn all of these vectors around, but also for the coefficient we have to take the conjugate transpose. And here this means that we will get minus I times 1. So what will we get? So I have a half, I will square it, I can move it up front, I get a quarter. And here we have 0 with 0, minus I 1 with 0, minus I 1 with 1, plus 0 with 1. So remember that the elements of the standard basis are orthogonal to each other, which means that this here is 0 and this here is 0. And the vectors have length 1, so this here has length 1 and this one has length 1. So what do we get? We have 1 on 4 times 1 minus I. So remembering the definition of this, namely a half times 1 minus I, 1 plus I, we see that we have a quarter times 1 plus 1, which is 2 over 4, which is a half. So of course, you could also now compute the probability of getting outcome minus. And if I were to do that, again by our rule, the probability is given by the inner product between psi and minus. Because probabilities should add up to 1, it's clear that what we should be getting here is also a half. And I encourage you to do this calculation. Let's consider one more example where we measure two qubits, which are indeed in the famous EPR pair. We've seen this before, and now we will measure it in the standard basis. So this was the EPR pair. And we'll measure it in the standard basis, given by 0, 0, 0, 1, 1, 0, and 1, 1. So these are the elements of the standard basis. And now let's apply our rule to find what is the probability of observing measurement outcome 0, 0. You've probably already become an expert at this calculation. So what we have is 1 over square root 2, 0, 0, plus 1, 1, with 0, 0, which gives us 1 over square root 2, 0, 0, with 0, 0, plus 1, 1, with 0, 0, and we square the whole thing. So again, these are our subitons, so this is 0, vectors have length 1, so this gives me 1, so this is 1 over square root 2 squared, which is a half. A similar calculation would show us that the probability of obtaining outcome 1, 1, which is given by the inner product between psi and 1, 1, is again a half. So we'll see that actually for this state, not all elements of the standard basis are actually possible to occur at outcomes, because we also have that these guys must add up to 0. So even though I guess we can see this from the rule that probabilities add up to 1, you should do an independent calculation to convince yourself that this is really true. So we've seen now some more examples of measuring qubits in the basis.